Friends, today we'll go for the next concept, that is different electric materials. Okay. So first we'll go for ferroelectric materials. What does this ferroelectric materials is? So we know that in the last class we learned regarding dielectric materials. So when dielectric materials, so there was polarization of the ions, so plus minus like this whenever the electric field is applied. So same thing here also in ferroelectric materials. We know that they are arranged electrons in very in this way, and they terms to be very good magnets even the field is removed. So why they are termed as a very good magnets even the field is removed? Because there is a spontaneous polarization in this. So we can see the spontaneous electric polarization is acquired whenever we go for the applied whenever we the electric field is applied. Okay, the field is applied, and these materials, ferroelectric materials, they show this curve, polarization curve like this. Okay, so the so even if and they show the reverse polarization also. So this is very much, it is called as the hysteresis. Okay. Hysteresis curve. So ferroelectric materials, they show the hysteresis curve like this. So if the polarization versus if you go for the field some electric field or electric this is EMF is being applied here. So you can see that these materials, they show hysteresis loop, that is the polarization of the is acquired here, spontaneous polarization, and it reaches to a maximum upfield here, that is called PS. PS nothing, PS is the thing but saturated polarization. And then after again, if the field is been decreased here, so you can see here the polarization decreases, and this is called PR, remnant polarization. It comes to the zero here, remnant polarization. And you can see even when it comes to zero field, so you can see some of the material is showing the polarization here. So electric is generated here, so still it is showing here. That's why even if the field is removed, this will show the magnetic field. Why? Because even if the field is been made to zero here, we can see the remnant polarization, still it is arising here. And again, if the field is taken down here, so we can see it the hysteresis loop comes here, and you can see here PS in the negative phase, which is minus saturated polarization, and this is called coercive field. Okay, at zero, and then again you can see. So like this, if I go for A, B, C liming here, so A can, you can see here it's a saturated polarization, then B remnant polarization, then C coercive field here, so it comes here. Then D, I can take it as a negative saturated polarization, so it negative saturated polarization. And as I increase again the field, you can see polarization increase, and it comes to E here like this. So again, uh, remnant polarization in negative. Then F, it comes to coercive field, negative coercive field, and finally it comes to Z. Okay, that is your again saturated polarization. So that means this is called total from A to G, we call it as a complete loop, hysteresis loop. So we call this as a complete hysteresis loop. Okay, so from 0 to A to B, B to C, so there is no repetition here. So total, so this is how the ferroelectric materials works on. So how they show the hysteresis loop here. The best example for this is barium titaniate. So that temperature, the TC 120 degrees centigrade. Okay, so this is, and second example, TC is Curie temperature 0.20 degree. Then potassium niobate NbO3. This is also a best example for ferroelectric material. Then potassium dihydrogen phosphate, lead titanate also. Okay, calcium. Yes, but this is not the ferroelectric material, calcium titanate, because barium is a bigger in size, and they can stretch the crystal structure to from minus 18 to 24 plus 24. So where titanium oxide bond length will be more, and titanium can be easily circulated towards this crystal structure, and that's why this may act as a ferroelectric material. But this is not a ferroelectric material, calcium titanate. So they may ask this. So calcium titanate is not a ferroelectric material. Yes, okay. So this is how the ferroelectric can be discussed here. The one more material comes here is pyroelectric. Pyro itself says that's a heat. Okay, so here we can see that like here ferroelectric metal, the field versus polarization. So here temperature is important. Pyro means temperature, and as you increase the temperature or decrease, there is a polarization. So here also net polarization, spontaneous flow is not equal to 0. That means even if you remove the field, suppose it will show the polarization like here, but here it is big. Even if you remove the field, there is a big polarization, still it requires here Ferro, but in Pyro, so it is less. So it will have the polarization even the field is removed. That's why spontaneous polarization is not equal to 0 here. Okay, and this depends on what temperature. So as you increase the temperature, polarization decreases like this. It is not reversible like it will not show like hysteresis like in ferroelectric, but so this is decreasing as you increase the temperature, so polarization decreases, and it is given by delta P is equal to nu delta T or sigma delta T, where what is the sigma or nu? It is nothing but ferroelectric constant. Okay, so delta T is change in the temperature, P is change in the polar. As you change the temperature, polarization also changes. Example here, zinc oxide. Okay, woodside structure it shows zinc oxide, or even barium titanium. So all ferroelectric materials are we can say it's a pyroelectric like this. Okay, next last one is the piezoelectric. So piezoelectric is mechanical stress. So as yes, so main here is non-centro symmetric point group is shown here. So when you give the mechanical stress here, so you get the electric current here. So that's we call it as a piezoelectric. So best example is here quartz. So when you apply the mechanical stress at this center 100, so you can see that this will going to acquire the piezoelectric, but not this. Okay, 001 if I apply stress, it will not show the electric current. So this is what, and the best example for this is tetrahedral zinc oxide or zinc sulfide, the best example to show the piezoelectric, because when you apply the mechanical stress over this will distort, tetrahedral structure will distort, and the electric current will be shown here by this. So that's a type of this we call as a piezoelectric. The best example PZT also comes in there. So PZT, so lead zirconium titanate, lead zirconium titanate or the lead titanium titanate. So it is given by P is equal to D sigma, where P is nothing but polarization, D is piezoelectric coefficient, and sigma, okay, piezoelectric coefficient, and this is the stress, mechanical stress, and this is used in most of the transducers. Okay, piezo earphones or loudspeakers and even cigarette lighters, so they use this material, piezoelectric material. By applying the stress, the current is been generated here. Okay, and if you see the relationship between ferro, piezo and pyro, so you can see that the subclass of piezo are pyro. Okay, on the subclass of piezo they are also act as a pyro. Okay, so spontaneous polarization is observed here, and some of the pyro are ferro, some of the pyro they act as a ferro, and but ferro are both, so pyro and piezo. So ferro materials can be both pyro and piezo materials, but pyro also is a piezo materials. Okay, pyro can also act as a piezo, but piezo, but most of the piezo are not the pyros. Okay, so most all the piezos, so all the piezo materials are not the pyro materials, are not the pyro. This is how we can bring the relationship between the AB, that is ferro, and pyro and piezo materials. And if you see the application of pyro, so they are used in the IR radiations. Okay, IR detectors, IR radiation detectors, it is been used. And ferro materials can be used in ceramics and capacitors. Okay, so this is the application of ferroelectric materials we can use. Then pyroelectric we can use in the IR detectors, like piezoelectric can be used for transducers, earphones, loudspeakers, cigarette lighters, so like this. So these are the different applications of these three materials. Okay, so here we complete the different types of materials here. In the next class we'll go for the next, that is superconductivity of the unit 4. Thank you.